Hello, welcome back to your physics teacher with me, Mr. Morales, and in today's lesson we're going to be looking at the final question from section 1.1. And this question is actually really difficult because I know in grade 11 we didn't cover it at all. So make sure that you watch it to the end, and that way you're going to be learning a couple of new things from this question alone. If you do need a bit more support with motion graphs, you might want to check out the previous grade 11 videos that I made before, and that way you have a stronger foundation to work with. So let's get started here with question number 9. Study the graph in the figure 14, and they want us to determine the average acceleration for the entire trip. So first, let's sort of see what kind of graph they give us. They gave us a velocity versus time graph. Positive values is saying that it's moving forward, the start of the race at time 0 and the end of the race at time 10. Okay, but notice that this graph for velocity time graph is curved. So that's what I was saying, that this is actually new. I know in grade 11 we never had a curved velocity time graph, because this would suggest that the acceleration is changing with time. So usually the acceleration time graphs are always horizontal lines. But now, because the acceleration is changing with each second of time, we suspect it might be diagonal. So let's confirm this by going through this question. And part A, the first thing that it asks us to find is to determine the average acceleration for the entire trip. So the average acceleration is the change in velocity over the change in time. And because acceleration is a vector quantity, that's why I put the arrowhead on top. Now, another way of doing it is to think of the graph that we're given, velocity time graph, and the slope of the velocity time graph gives us the acceleration. But in particular, whenever you take the slope of the secant line, that gives you the average acceleration. So let's draw our secant line for the entire trip. So it's just the line that connects the endpoints. Okay, so this has let's put the endpoints. What is my final velocity, which is at the end of the race? My final velocity is 0. My initial velocity was 50. Oh, my doggy wants some attention too. Yeah, I'm doing a video right now. Okay, I think she's calmed down now. Alright, the final time in this case was at the 10-second point, and the initial time was at 0. So in this case we have negative 50 divided by 10, so this would be negative 5 meters per second square. Alright, so in this case, the negative, it indicates that the direction is backwards, because here in our graph forward was associated with positive, so negative would be backwards. So we could write this as 5 meters per second square backward. And that's our average acceleration during the entire trip. So that was a good approximation, but like we mentioned before, the acceleration is actually changing at each moment in time. So I suspect that they will get to this in part B. Yeah, part B says to determine the instantaneous acceleration at 3 seconds, 6 seconds, and 9 seconds. So if you recall from question 8, if you watched the previous video, that at 3 seconds 6 seconds and 9 seconds. So in other words, at a moment in time, you can just calculate the tangent, the slope of the tangent. So in this case, to find the instantaneous acceleration, we find the slope of the tangent line at those specific times. So instantaneous. So here in part B, they want us to calculate the instantaneous acceleration, which we can do by taking the slope of the tangent line at each of those specific times. And what we need to do then is, from our graph, we need to approximate the tangent at those specific times. So at 3, 6, and 9. So at 3 seconds, we want to draw the tangent at the 3 second mark, which is, we take the point 3, and the one closest to it is 3.0001. We connect those two with a line, and that's our tangent. And to calculate the slope of this tangent, you want to pick the point that we were given, which is at the 3 second mark. So at 3 seconds, and then approximately the velocity at that time is 47. And the other nice point that we can pick is for our tangent line to be touching the grids in a point that's easily read, which is approximately at 8 seconds. So we're going to use those 2 points to calculate our instantaneous acceleration at 3 seconds. So instantaneous at the 3 second mark is going to be the change in velocity over the change in time. But in this case, the final velocity will be 30. Initial one was 47. 8 minus 3. So what is this approximately? 3.4. This makes sense because we expected to get a negative number, and the number should have been less than 5, because 5 was the average acceleration for the whole time interval from start to finish. And at the very beginning of the race, the velocity is not very steep, the curve, so the acceleration should not be such a high value. So 3.4 makes sense. We suspect that the acceleration value is going to increase for the later times, say at the 6 second mark. So at the 6 second mark, let's draw our tangent. And first we pick the point at the 6 seconds, and then we pick the point very close to it, and we draw the tangent line. I cheated there a bit to pick a nice point, which is 8 and 20. And this one was 6 and 30. So let's find our instantaneous acceleration at the 6 second mark. Is the change in velocity, change in time. 20 minus 30. 8 minus 6. So see, we were correct. The acceleration does increase. So it's negative 5 meters per second squared. So the acceleration is increasing. Now the next time that we want to look at the instantaneous acceleration is at the 9 second mark. So once again, we pick the point at the 9 second mark, the one close to it. So at 9 seconds, it's approximately 10. And we're going to cheat a little bit, and we're going to say it touches 10, which is close to 0. Close enough. For tangents, you could be slightly off, so I cheated a little bit only. So the instantaneous acceleration at the 9 second mark is going to be 0 minus 10, 10 minus 9. Right? So in this case we get negative 10, which we expected it to be negative, and we expect it to be bigger than negative 5, because at the very end this graph is changing its velocity very rapidly. So the acceleration should be at the highest at that area. So these are the three instantaneous accelerations, and we just found it by taking the slope of the tangent, by approximating tangent lines. So your values are going to be different than mine, but the sign should be the same, and the magnitude should be more or less within one or two values within what I got. So this shouldn't be so different. And for part C, they want us to sketch a qualitative acceleration time graph of the motion. So this goes back to grade 11. So in grade 11, what I usually like to do is draw my two graphs one below each other. So we go from VT and we want to go to AT. Our velocity time graph looks something like that. And we have the instantaneous acceleration for 3 time intervals, right? Yeah. Not time intervals, 3 instants in time. So acceleration at 3 seconds, acceleration at 6 seconds, and acceleration at 9 seconds. Negative 3.4, negative 5, and negative 10. So how we draw the velocity time, how we draw acceleration time graph from velocity time graph, we're going to try to use the same time in each graph to make sure that we correspond each of those values. So what I mean by that, if you see how they're lined up below each other, we're going to be looking at the 3 second mark, 6 seconds, and 9 seconds. And then we plot the values. So at the 3 second mark, the acceleration was negative 3.4, so it's on the negative axis, so that's why it's below. At the 6 second mark, the acceleration is negative 5. And at the 9 second mark is negative 10. So all we have to do now is just connect them with a line of best fit, or curve, but in this case it looks linear. Maybe, well, my axis was not really nice, because from 3 seconds to 6 seconds is much bigger than between 6 and 9. So mine's a little bit off. So you might want to make a better scale for your sake. But this gives you the right type of information, because here we see that the velocity, the values of it are getting closer to 0, but the acceleration, which is the slope of the tangent, was getting more steep, so it was getting bigger and bigger. So here we get a linear graph. Again, your values might be slightly different, but at the end the shape should be the same. And the reason why I approximated the acceleration to be 0 initially, we didn't have other information to go off, so that's one assumption I had to make. Okay, yeah, that's it. So this section was pretty difficult. Physics, grade 12, stays hard. It doesn't really get easier. But I'm here to help you out, so make sure you subscribe, and then I'll be as helpful as I can be. Until next time.